Hello and welcome to WCT's technical webinar series. In this webinar, we are going to talk about full wave-based field circuit co-simulation for ESD problems. The outline of this presentation includes brief review, modeling ESD problem, and challenges for ESD simulations. Let's start with the review section. ESD stands for electrostatic discharge. It is typically a transient electromagnetic behavior between two objects that has high voltage difference. And when they approach each other, a sudden momentary current will flow from one to another and cause the sparkling effects. Take this power box as an example. It has very complicated CAD model, and a sudden electric current is injected to the top side of the box. The current will spread not only on the surface of the box, but also flows inside, causing oscillations and leads to interference. In the situation when critical controlling signals are being sent from one circuit to some devices without EMI protection concern, such signal is very likely to be interfered and cause 0 and 1 logic error and leads to system failure. These failures may cause equipment malfunction and network downtime, thus causing production losses of multiple billions of dollars annually. Therefore, from portable consumer electronics to industrial automation, process control systems, and military and aerospace applications, every electronic manufacturer must consider ESD during the design stage. Due to this need, lots of ESD testing procedures are defined by engineers and were summarized as standards, which leads to a much broader EMI/EMC testing category. There are several standards to perform all kinds of EMC/EMI tests. In our particular interest, device level and system level testing are often being referred to. Device level testing includes human body model, machine model, and charged device model. From the table, we can briefly compare their differences. Among the three, HBM has the highest voltage level. It can reach up to 15 kilowatts. The current amplitude varies from 1.5 to 6 amperes. CDM has the sharpest pulse, and HBM is typically slow. All of these models will cause junction damage. On the system level side, there are ESD air gap and contact tests, EFT and lightning tests. Both power and signal lines are included, and their voltage level are typically a couple of kilowatts. Other than the IEC standard, the military standards such as 461E give more strict and detailed definitions. Emissions and susceptibility requirements span from 30 Hz to 40 GHz. Power line, EM field, cable, antenna, and other ports are all included for this testing. ESD testing is a mandatory step, but also a money-burning stage. It is nice to use CAE, computer-aided engineering tools, to predict the behaviors on the computer screen rather than seeing a failure device burned down in the lab. However, modeling and simulating such a process is challenging due to its multi-physics and multi-scale nature. Physical tests and measurements are still the essential part before the product delivery, but when troubleshooting a failure, trial and error approach is very costly and low efficient. That is where simulation can fit in to remove the pain of redundant and tedious setup and calibrations. It is even more convenient to use the CAE solutions for what-if tests, when certain changes need to be made on the device under test. Essentially, using the CAE solutions for the product development workflow will dramatically reduce the cost, speed up the process, and minimize the risk of hardware testing failure. Next, let's move to the presentation of modeling the ESD problem. The first important factor needs to be considered in the EMC/EMI problem modeling is the initial conditions of the system or device under test. Typical initial conditions can be categorized into neutral, charged, and biased. Each of them will have dramatically different responses to the external triggers, such as single pulse, train-up pulses, and constant switching. Take the right figures as an analogy. Neutral system will always try to return to its neutral status after a period of time when an external pulse is applied. This is more like a well-grounded system in the eyes of EMC/EMI engineers. Charged system is more similar to the situation when the ball is on the top of a curvature, where any external force will make it fall down and never return back to its initial condition. This is more like the situation for HBM and charge device model. Bias system is conditionally stable and has some limited tolerance of the amplitude of the external forces, but not too much. This is very similar to the situation when semiconductor transistor is biased and try to avoid the saturation. When modeling the EMC/EMI problem, there are arguments about which type of the EM field solvers are more appropriate about EMC/EMI problems. Typically, time domain solvers is good at capturing the transient behavior such as lightning strikes and ESD. Frequency domain solvers are more efficient in solving steady system status such as emissions. When dealing with the practical EMC/EMI problems, none of the above mentioned can handle all cases in all situations. Some preliminary understanding of the problem nature must be conducted before jumping into the simulation. The second factor for modeling ESD problem is the excitation types. In general, there are various excitation types for EMC/EMI problems. For example, point dipole sources are very typical for receiving antenna sensitivity testing. Plane wave and beam illuminating are excitations that come from the outside of the computational domain, mimicking the situation where the sources are far away, like radar. In more general cases where the incoming wave is not describable with mathematical formulations, near-field ingestion can be used to load in the user-defined or measured wave patterns. Guided waves will have modes in order to transmit the full energy into the system. Thus, waveport is also typical when waveguide excitation is applied, such as coaxial cable and rectangular waveguides. A circuit port is also very useful in representing an injected current or voltage to a device or system. Especially for ESD problems, circuit port has some unique advantages in modeling the source excitation. This will be covered in the following slides. In particular, the ESD sources are complex to model, such as lightning strikes, ESD guns, and signal generators. The key question to ask is what are the factors that we really should care when dealing with these sources? For the device or system under test, the signal transient behavior, total amount of injected power, and touching approach are the typical parameters for ESD analysis. Another key factor, which is often not being considered sufficiently, is the multiple reflections between the DUT and the source due to impedance mismatch. Multiple reflections will severely disturb the responses from the system, and thus it will be hard to extract the true system behavior from the mixed responses. Consequently, it is very important to ensure that reflection only occurs once from the DUT to the source and never get back from the source to the DUT again. Let's take a look at this example of which a lightning strike is hitting onto a 20 meter by 20 meter by 7 meter building. It is obvious that there is no need to model the cloud and the sky, but the touching point and the total amount of current being injected into the building matters. Here we use an equivalent circuit current source to represent the lightning strike current, and link such circuit port as a source in the 3D EM field simulation. The transient signals we used is a typical lightning strike signal from the IEC standard. The next example is the HBM testing on the PC box. Again, there is no need to model the ESD gun on the human fingers that are touching the box. What really matters is the transient signal, voltage between the two objects, and the touching location. These input information can be easily represented by a circuit voltage source that is linked within the 3D EM field simulation. And the result reveals very detailed information of how such ESD current is spreading out through the entire box. Next, let's take a look at the transient signal signature when modeling the ESD problem. ESD process is typically a transient process. Thus, the signal signature is very important for the analysis. Wavnology supports various signal types. A user-defined signal can also be imported to the simulation. SPICE model signal generator can also be implemented in the software. The current challenge for modeling the EMC-EMI problem is the long train of pulses. Note that these train of pulses are not an infinitely periodic signal. Thus, their spectrum will not be at discrete frequency points. When nonlinear system is under testing, it will bring complicated responses. If the problem does not contain extremely long train of pulses, current solution can still handle it pretty well. For example, for these HBM, MM, and CDM tests, their transient signals are shown on the left column and their spectrum are shown on the right. It is very important to understand the signal signature in time domain and their bandwidth in the frequency domain. Among the three tests, CDM can excite frequencies up to 2 GHz, where HBM and MM only covers up to 25 MHz and 40 MHz respectively, which is much smaller than the CDM. For IEC system level tests, there are also various signal signatures for different E3 situations. Their bandwidth are typically under 30 MHz. In summary, the 6 types of IEC test standard we referred has 3 key parameters for us to understand. Number 1 is the pulse time window, ranges from 2 nanoseconds to 1000 nanoseconds. Number 2 is their bandwidth in the spectrum, ranges from 25 MHz to 2000 MHz. These 2 parameters are very typical in describing the excitation pulses. There is a third important parameter to characterize the excitation pulses, which is not quite oftenly be aware of. That is the spatial wavelength that the pulse will excite. The wavelength can be calculated by dividing the speed of the wave with the frequency of the signal. Assuming all these excitations are applied in free space or air, the wavelength with the 6 types of pulses ranges from 15 centimeters to 12 meters. In general, if the object size is larger than a half of the wavelength, it is very likely that such pulse will excite the resonant waves within the object. Such resonances may lead to high emissions and interfere its internal devices. So an intuitive judgment of whether the device under test will resonate with the excited pulses can be made by comparing their sizes with the wavelength. For example, for most of the PCB devices, its dimension is millimeter to centimeter range. Compared to 12 meter, it is E small problem. Most of the field behavior will be evanescent waves, which means the field level decays exponentially. But if compared to 15 centimeters, it is not. Radiation may occur. For chamber, vehicles, and other platforms, they are in the meters range. So when hit by a 25 to 30 MHz pulses, it is very likely that resonances will occur. The next important consideration for modeling the ESD problem is the combined field circuit nature. Since ESD is a transient process, and typically causing junction damage to the semiconductor integrated circuits, thus when modeling the ESD problem, besides the field behaviors, one cannot ignore the circuit reaction due to the external inputs from the EM field environment. This naturally forms a problem that involves both EM field simulation and circuit simulation. A very practical issue during the ESD failure is when the PCB plus IC are burnt down due to the ESD, It might be one of the capacitors on the PCB or some junction damage inside IC. But which one could it be? It would be nice to use Field Solver to simulate the EM field behavior in the 3D structure, and use the Circuit Solver to simulate the voltages and currents of the internal IC structure. Wavnology combines these two solvers for this purpose. As can be seen in this example, an IC is modeled with a SPICE circuit with 16 ports that are linked to the 3D structure, and an excitation is applied to one of the traces and distributed to the other 15. The coupling between the traces and the circuit impacts can be all simulated within one solution. If we apply the circuit source to model the ESD injected current, using the user-defined CDM signal to model the transient signature of the ESD pulse, and take the circuit and traces into account, we can simulate the entire process using the techniques mentioned above, and analyze the ESD behavior from the field level on the board down to the circuit level inside IC. When a surge signal is applied, which spectrum is concentrated at a low frequency, its wavelength will be much larger than the board size. Oscillation will not be excited. Most of the energy will be concentrated on the contact point and decay very fast as it spread deeply into the board. Consequently, the interference mainly located at the beginning part of the signal. Engineers must predict these behaviors to apply appropriate solutions. Besides the discussions we already covered, ESD problems are still quite challenging due to the following reasons. First of all, ESD problem is typically a system-level problem. Modeling and simulation can only take care of a portion of the entire system. Engineers using CAE tools has to manually simplify the problem a lot in order to be able to simulate them. This requires a lot of experiences to judge which component is sensitive to the EM field. Second challenge is the material. ESD problem has a wide range of types, especially when human body is involved. Modeling the material is quite challenging. The third challenge is the nonlinear effects from semiconductor diodes and transistors. These devices will generate harmonics, power-dependent responses. Novel devices even have memory over time. Thus, analyze the time variant and nonlinear systems is quite challenging. Take this simple example. A varactor diode is mounted on one side of the ring. As we increase the input power level at 0.7 GHz, we can clearly observe the harmonics generated at 1.4, 2.1, and 2.8 GHz. These harmonics are unwanted when the device is required to pass the emission test at a wide frequency range. When the varactor has mixed inputs, such as 4 GHz and 5 GHz in this case, the output is more complicated. The uplink frequency at 9 GHz and downlink frequency at 1 GHz has the output. However, high-order harmonics occurs at almost every single gigahertz in the spectrum. What is even more complicated is when the input signal has a continuous spectrum, in this case a Gaussian pulse. Then the output spectrum has much wider responses. In this case, it's from 0 to 6 GHz, when the input frequency range is from 0 to about 3 GHz. Due to the above reasons, when applying the ESD protection circuits, we need to be very careful of the nonlinear behaviors. In summary, we have covered several major aspects about ESD problem modeling. For system status, frequency domain solver is good for solving its initial or steady state conditions. Time domain solver is more convenient for capturing the transient process behavior. Typical interference can be conductive immunity and RF community. The challenge